did not know yesterday yet what to talk about, so I decided to talk about the atoms of space, which are the smallest open set in the topology, which you have in a delta set. Delta sets, here a reminder, is a very nice geometric construct where you have naturally already exterior derivatives, so you have Stokes' theorem, etc. You have physics, and so you have a Dirac matrix, you have a Laplacian, so you have spectral properties, all kind of nice things, and you have also a natural topology. There's a natural partial order on this G coming from the structure of the D, which tell what elements are faces of some other element. Then you have also a dimension function, which is needed in general. It's not needed in a Simplicial complex, but in general it's needed. And so this topology is not Hausdorff, but we have nice notions of spheres. So we have unit sphere, we have an open unit sphere, a closed unit sphere, and they allow us to work like in Euclidean spaces. The geometry we usually look at, we don't have linear parts, but we have nice spheres. We have also an incidence relation, and we have an incidence calculus, which doesn't exist in the geometry which we usually deal with for manifolds, so I'm not aware that anything like this has been defined. So there is a nice structure. I summarize this here a little bit, which Laplacian, type of Laplacian, which is always invertible. So the vacuum is stable. We have implicit function theorems and not hard implicit function theorems. It's very, very exciting that things are just working very nicely here. We have also the inverse explicit formula for the inverse for the green functions, which is a problem in the continuum, right? In the continuum, the green functions are singular. The 1 over x potential which you have for gravity or for electromagnetism comes from the fact that we have not invertible Laplacians. And here in this case, I was actually looking at the case, how far can we push theorems, or how far can we push especially the calculus, you know, this connection calculus to delta sets. So almost all sets in this morphological box, right, from Zwicki has defined kind of this method to think, is that you look at kind of, I'm thinking in terms of theorems, which theorems work and how far can you push them. And so differential geometry and algebraic topology and calculus work very well, and generalize even to signed delta sets, which is really the ultimate structure. You don't want to work only in positive integers, you want to work in all integers, and that's naturally also here. This space, this topos can be extended to a ring, so you just make the this monoid structure of the coproduct, you make it to a group, and then you have a ring, and just you define things in such a way that, for example, you know, Gauss-Bonnet works, curvature and everything you can extend to negative space. So this is kind of the way you want to push it as much as possible, the theory. And in this case, with a connection calculus, there are some kind of some resistance. And one of the things is with atoms, when you look at an atom, then everything is connected to each other. So you have this connection matrix, how I defined it in 2016, is not invertible, obviously. But in 2020, I saw that it was the wrong definition. You have to take the Euler characteristic of the intersections of the cores, and the intersection of the cores are, in general, when you take the delta set or kind of more general set, it's not 1. This is an integer, but it shows that it's kind of natural, because this is kind of like the stable and unstable manifold in hyperbolic dynamics, right? The core, these are all the sets which are contained. This is in this poset. In every poset you can do that. And then the sets which contain it. So these are defines your this duality between open sets and closed sets. And so you can then also, was very important also for higher characteristic, to push things to Wu characteristic, higher characteristic, and then there are k-point, you know, k-point correlation functions, green functions, which add up to the Euler characteristic or to the energy you define. All these can be generalized also when you don't take -1 to the r as a kind of a energy, but you take more general energies, division valued functions, for example. This is kind of shows that with the right definitions you can push things further, and so, but in general it's actually not true that this energy theorem holds. So the energy theorem, I was very excited in 2016, the sum of the entries of the green functions, all the potential energies added up. The green function tells you what the energy between two parts of space is. This potential energy, if you add them all up, you get the Euler characteristic, or the higher characteristic. And that's for Simplicial complex. That's actually the simplest case, when you have a one-point correlation. 1 point, then you take the sum of the omega x and the Euler characteristic of the atom, and you get the Euler characteristic. This is kind of the simplest case, but then we have it in 2 points is kind of maybe the most interesting case in physics, because you look at 2 points, how they interact. And in this case, that was this observation that the sum of the green function entries is always the Euler characteristic. But it doesn't hold for general sets. For general sets, this is false, and maybe here I have an example. Right? If you take this comma space, kind of the simplest, one of the simplest spaces you can imagine, a point and an edge. So this is actually in a tree, for example. If you take a leaf and you take the open set of the leaf itself, that's the open set. So this has Euler characteristic 0 because there is 1 point and 1 edge. And so this is the connection matrix defined now with this definition. Actually, I realized in 2020 that this works for any set of sets. Like the determinant formula holds, the unimodularity holds for general set of sets. But the energy theorem, the sum of these things is not the Euler characteristic 0. So that doesn't work. So there are some things which might actually need an adaptation of the definition, or it just doesn't hold, by nature. Actually, how I got into this, kind of this week, I was making experiments with open manifolds, which are kind of given by SAR. If you have a manifold, closed Simplicial complex, which is a manifold, and you take any function which takes finitely many values, then you can define, if you take k plus 1 values from 0 to k, then you have level surfaces which are always either empty or always are d minus k manifolds, always. And that's really exciting because we can build manifolds, but these are a priori open sets, as we have seen. And then we can look at, this is a delta set, and we can think about this as a manifold because its barycentric refinement is a manifold. We could also just extend the notion of manifold also to delta sets and directly kind of see, don't worry about making a barycentric refinement. And but what I actually was wondering this week is whether I can find examples where the manifolds are kind of new. They are not really coming from Simplicial complexes. Let me stop it now.